Howdy. This video is on the rate constant and the Arrhenius equation. The rate constant is part of the rate equation and greatly affects reaction rates. By understanding the effects of rate constant, we can better understand reactions. The Arrhenius equation illustrates how the rate constant is affected by both temperature, the activation energy of activation, and we also talk about how catalysts affect the energy of activation. And so it is fairly important. What you should be able to understand after watching this video is that you should understand the following terms: reaction coordinate, activation energy, transition state. You should understand how the rate constant rate reaction are affected by temperature and the presence of a catalyst. You should be able to understand that a catalyst is not consumed by a reaction, it just lowers the activation energy. It actually provides an alternative pathway that has a lower activation energy. And so one way to think about it is, say you have a boulder and a hill, and you want to get the boulder over the hill to the other side. Well, the distance between where you're at and the top of the hill, that's the activation energy. And so you have to have enough energy to overcome that barrier. And according to the Arrhenius equation, that's what determines the rate constant. It's just the barrier between the reactants and what's referred to as the transition state. And again, this is the activation energy.
When a fluoride ion approaches a methyl chloride molecule, a bond begins to form between the fluoride and the carbon. The molecule's carbon-chlorine bond lengthens and becomes weaker. The energy of the system increases. As the carbon-fluoride bond forms and the carbon-chlorine breaks, a configuration of maximum energy is reached, called the transition state. As the reaction proceeds to completion, the energy of the system decreases.
This is a really cool video. And so what you notice is that the reactants are relatively stable compared to the transition state. The products are more stable than the transition state. The transition state is the least stable configuration. It's actually where the carbon, in this case, has 5 things bound to it. So it's very unstable. And so to go from the reactants to the products, you have to overcome this barrier. The barrier is the activation energy. The top of the barrier, you have the transition state or the activated complex. So this gives you another picture. And so the y-axis is the potential energy, the x-axis is the reaction coordinate, so how the reaction proceeds. You have the reactants on the left, the products on the right, and then the transition state on top. And so that activation energy is difference energy between the transition state and the reactants. Now the larger the activation energy, the slower the reaction, and what we'll see is that the lower the rate constant, the smaller rate constant. The difference in potential energy, delta G, of the product's reactants determines the equilibrium constant. And so another thing that's very important to understand from this graph is that, so the activation energy determines the rate constant, the delta G determines the equilibrium constant. And so thermodynamics, delta G, equilibrium constant, different than kinetics, which includes the rate constant and the rate. Okay, so activation energy determines the rate constant, delta G determines the equilibrium constant, and the two are very different, very separate. And so we have this plot, and again it shows you the energy versus reaction coordinate. Now on the right we have a plot that we use for equilibrium, where we have the energy and the reaction quotient. I don't want you to get these two plots confused. On the left, the reaction coordinate is kind of like the step how one or two molecules interact to form that, for the reaction to occur. That's what we mean by reaction coordinate. So we're not talking about a lot of molecules. We're just talking about the molecules, one reaction involved in a single reaction. On the right, remember the reaction quotient is products of reactants. Coefficients become exponents. Pure solids, pure liquids don't appear. And so please make sure you understand the difference between these two plots. Now if we take this plot a little bit further and look at two examples, and so on the top we have a delta G is less than 0. On the bottom we have the delta G is greater than 0. And so on the top one, the chemical potential energy of the products is less than the reactants, and so the equilibrium constant should be greater than 1. On the bottom one, the chemical potential energy of the products is greater than the reactants, and so the reactants are more stable, and so the equilibrium constant is going to be less than 1. Now the activation energy, larger activation energy, the bigger the hill that you have to go over to cause the reaction. And so larger the activation energy, the slower the reaction, the smaller the rate constant. And so on the top one, we should expect that the rate constant is going to be smaller than on the bottom one. And again, remember activation energy is just the difference in energy between the transition state and the reactants. And so in general, the difference in activation energy is why reactions vary from very fast to very slow. The higher the activation energy, the slower the reaction. The activation energy also causes reactions to go faster at higher temperatures. And so if you remember, in terms of equilibrium, how temperature affects reaction depends if it's exothermic or endothermic. For endothermic processes, the Equilibrium constant increases with increasing temperature. For exothermic processes, the Equilibrium constant decreases. For kinetics, it's completely different. Higher temperature always means faster reaction. And so a question we could ask is, for the reaction corresponding to the profile shown on the left, is the Equilibrium constant greater or less than 1? Well, again, the products are more stable, and so we'll have more products at equilibrium. Equilibrium constant is products of reactants, and so K should be greater than 1, which is larger than the rate constant of the forward reaction or for the first or reverse reaction. And so again, it's going to be the transition state, the energy of activation. And so for a forward reaction, you have the difference between the transition state and the reactants. And for the reverse reaction, the activation energy is between the products and the transition state. And so the reverse reaction, you have a larger activation energy, and so that would be slower. For a forward reaction, that should be larger. And so the activation energy for the forward reaction is smaller than the activation energy for the reverse reaction. Hence, the rate constant for the forward reaction should be larger. The forward reaction should be faster. Which has a large Equilibrium constant between these two plots. And so for both of these, the products are more stable, and so both of them, K should be greater than 1. Now, the difference in the energy for the bottom one is larger than for the top. And so the bottom one should have a larger Equilibrium constant, assuming that the scales for these two plots are the same. Which has a rate constant which has a larger rate constant for the reaction, and so that corresponds to a smaller activation energy. And so again, that's the bottom one. And so again, activation energy determines the rate constant of the rate. The difference in energy between products and reactants is what determines the equilibrium constant. Now it's kind of interesting, if we look at this reaction, we have methane plus oxygen goes to CO2 plus water, so it's a combustion reaction. Now we can think about this combustion reaction, the products are more stable, and so we'd say that this is a spontaneous process in terms of thermodynamics. It's not instantaneous, it's spontaneous in that it occurs without any outside intervention. And if you do not light a match, it will occur because the products are more stable, but occur very slowly. Now, if we do light a match, we can actually add some energy, helping the reactants get enough energy to overcome that activation barrier. Another thing to think about is, because of activation energy, that's why we can actually store fuel. If it wasn't for the activation energy, things would always go from high energy to low energy, and fuel would always combust because the products are always more stable.
Oxygen and methane molecules are mixed together in the same container, they collide. But there is no reaction until a spark or flame is added. Why? To react, the molecules must collide with sufficient energy to break the oxygen-oxygen bonds and carbon-hydrogen bonds so new bonds can form. The additional energy needed to break existing bonds and start the reaction is called activation energy. An energy diagram can help show these energy changes. Initially, the oxygen and methane molecules collide but do not have sufficient energy to react. A flame can supply the activation energy needed to start the reaction. At this point, bonds break and new bonds form in an exothermic reaction that releases energy.
And so it's an exothermic process, but again, for the reaction to occur, it has to overcome that barrier, the activation energy barrier. And when you light a match, you're adding energy, giving the molecules ability to overcome that barrier. And so actually, you're giving some molecules to overcome that barrier. They release more energy, and so then the reaction proceeds. And so again, fuels like methane, typically do not react without a spark or flame. Actually, maybe a small percent will react without spark or flame because the products are more stable. And so you typically have to add a flame to overcome that barrier. Now it's kind of interesting, there is something referred to as the autoignition temperature. And so if a fuel has a temperature that is taken to a temperature above the autoignition temperature, they will actually react spontaneously at that temperature. And so for methane, that temperature is 580 degrees Celsius. And so at that temperature, enough molecules have enough energy to overcome the activation barrier that the reaction proceeds rather fast. For gasoline, that autoignition temperature is actually 280 degrees Celsius. And so if you have a gasoline at that temperature, the reaction is going to be very fast without any spark whatsoever. And so in the methane, we saw an exothermic reaction that had activation barrier. Endothermic reactions also have an activation barrier. And so N2 plus O2 can go to 2NO. But again, for this reaction to proceed, you have to have enough energy to overcome the barrier.
And oxygen are continually colliding, but lack sufficient energy to react. Heat from lightning supplies the activation energy to break bonds, and new bonds form in an endothermic reaction that absorbs energy.
And so it's this barrier that actually determines the rate constant for the reaction. Now, a catalyst can speed up the reaction by lowering the activation energy and increasing the rate constant. And so in the black line for this plot, we have an uncatalyzed reaction. And then the red line, we actually have a catalyzed reaction. And so all that happens is the catalyst is providing an alternative pathway with a lower activation barrier. Now, sometimes what that means is that the catalyst will provide a place where the reaction occurs and stabilize the transition states. And so catalysts are not consumed by the reaction. They just provide an alternative pathway. And this is a really kind of cool reaction. And so we have hydrogen peroxide going to water plus oxygen. Now, when I start the movie, if you look carefully at the hydrogen peroxide in the beaker, you don't see much of a reaction. There's probably a small reaction, a very slow reaction proceeding. Now, the black stuff is manganese oxide. Now, when that's added to the hydrogen peroxide, the reaction will proceed much faster. The manganese oxide is a catalyst for this specific reaction. The catalyst for a reaction is very specific, and so a catalyst can catalyze one reaction but not necessarily another reaction. But when you add the manganese oxide to the hydrogen peroxide, the reaction will go much, much faster. I think it's like a factor of 10,000 times. Now, the cool thing is because the manganese oxide is not consumed by the reaction, you can actually filter off the manganese oxide and then use it over and over again.
Hydrogen peroxide in water decomposes slowly at room temperature. In the presence of manganese dioxide, however, the decomposition occurs much more rapidly. The reaction produces oxygen and water. The manganese dioxide is not consumed or otherwise altered by the reaction. It serves only as a catalyst and makes the reaction occur more rapidly.
And so again, basically what it's doing is just stabilizing the transition state, and that's bringing down the activation energy. Now, if you notice, it actually brings down the activation energy for the forward reaction. It also reduces the activation energy for the reverse reaction. Now, it's also kind of cool, in 1970s, there was a lot of pollution in cities, and people tried to address that. One way of addressing that is using catalytic converters in cars. And so in catalytic converters in cars, you can actually convert the CO into CO2. Carbon monoxide is toxic, it's poisonous. CO2 is not. CO2 is actually what causes drinks to be carbonated. You can also convert NO, which is toxic, into N2 and O2.
A significant source of air pollution in many cities is the emission of nitrogen oxides by gasoline engines. The problem is not as severe as it was a few decades ago, due largely to the advent of devices called catalytic converters installed in automobile exhaust systems.
And so the way this actually works is that you're going to have a metal dispersed on a ceramic inside the catalytic converter, and on these metal particles, that's where the reaction is going to proceed. And so basically the metal particles is just going to stabilize the transition state.
In a platinum-based catalytic converter, nitrogen monoxide molecules in the exhaust stick to the surface of the platinum. The molecule decomposes, each atom remaining on the surface. When another NO molecule comes to the area, it also decomposes, and its N atom bonds with the other N atom on the platinum surface. The O atoms also combine. The gaseous nitrogen and oxygen molecules then float away from the surface.
And so again, catalyst is not consumed by the reaction. It just stabilizes the transition state, lowering the activation energy of both the forward and the reverse reaction. There are also some natural catalysts. Enzymes are a natural catalyst in biological systems. Here we have chlorofluorocarbons. When they hit with light, they actually can break that carbon-chlorine bond and giving you the chlorine atom. The chlorine atom can then act as a catalyst for the destruction of ozone. Now, this was actually seen as a problem, and so most countries agreed to stop forming chlorofluorocarbons because it was depleting the ozone layer, and the ozone layer is what protects us from ultraviolet radiation. But this was a catalyzed reaction. The problem is the chlorine atoms can destroy tens of thousands of ozone molecules.
The stratospheric ozone layer, so important to life on Earth, can be depleted by catalytic chemical processes. In recent years, man-made chemicals have contributed to the loss of stratospheric ozone. Among the most important of these are chlorofluorocarbons, or freons. For example, freon 12. Chlorofluorocarbons, or CFCs, are very stable molecules in the lower atmosphere. Over a period of years, they slowly diffuse into the stratosphere. In the stratosphere, the CFCs are subjected to energetic ultraviolet rays that can cause rupture of a carbon-chlorine bond. The chlorine atoms act as a catalyst for the decomposition of ozone. Collision with an ozone molecule results in oxygen transfer, forming ClO and molecular oxygen. The ClO that is formed reacts with various species, notably atomic oxygen, to reform the chlorine atom and producing molecular oxygen. The sequence of reactions consists first of reaction of chlorine atoms with ozone, followed by the reaction of ClO with atomic oxygen. The overall reaction is just the decomposition of ozone. Atomic chlorine acts as a catalyst for the decomposition. Because the presence of CFCs in the stratosphere is capable of substantially reducing the ozone shield on which life depends, their manufacture and use has been greatly curtailed in the industrialized nations. Nevertheless, their effects on the ozone layer will remain.
And so again, the cool thing is people understood the problem, addressed the problem by prohibiting the production of CFCs, and actually stopped producing them, mostly. And in 50 to 100 years, the ozone holes should heal themselves. It's going to take a long time because the diffusion of the CFCs to the stratosphere takes a long time, and so there's still a lot of CFCs in the atmosphere. Now, the reaction that depletes the ozone occurs in two steps. First, you have the chlorine plus ozone going to ClO plus O2, and then you have the ClO plus oxygen going to Cl plus O2. Now, if you add these two steps, you get ozone plus oxygen goes to 2O2. And so you see the depletion of ozone. Now, the chlorine is the catalyst, and so the catalyst is there at the beginning, it's there at the end, but it's not in the net equation. It doesn't take part in the reaction. Well, it's not in the net reaction. It doesn't get consumed by the reaction. Now, the ClO is referred to as a reaction intermediate. Reaction intermediates are short-lived species that are formed by the reaction and consumed by the reaction. And so you see in the first step, the ClO is produced, and then the second step, it's actually consumed. And so they're only around for a short period of time. So please remember, catalysts are there at the beginning, they're at the end, not in the net reaction. Reaction intermediates are produced by the reaction, consumed by the reaction. They're unstable short-term species. And again, all that's happening is the chlorine is providing an alternative pathway that lowers activation energy for both the forward reaction and the reverse reaction. Catalysts speed up reactions by providing these alternative pathways. Catalysts are not consumed by the reactions. Industrial catalysts reduce the heat needed for reactions, for the speed of reaction, but does not affect the change in enthalpy of a reaction. That's important. The catalysts do not change the energy of the products or the reactants, and so catalysts do not change equilibrium constants, do not change the change in enthalpy for the reaction, but reduce the amount of temperature needed to cause the reaction to go faster. Catalytic conversions in cars reduce pollution emitted by cars. Enzymes catalyze many reactions in the body. Chlorine from CFCs can catalyze the destruction of ozone. Now with the Arrhenius equation, we can actually calculate the rate constant. And so remember, lowercase k is the rate constant, A is referred to as a frequency factor, E sub A is the activation energy, R is the gas constant, and T is temperature in Kelvin. And so we can actually calculate what K should be. Now it's also interesting, if you look at the exponent, E minus EA over RT, that's actually related to Boltzmann. It gives you the population of the reactant molecules that have enough energy to overcome the activation barrier, the activation energy. The A term is related to what percent of collisions have a correct orientation for the reaction to occur. And so the higher the temperature, the faster the reaction. The lower the activation energy, the faster the reaction. And remember, the larger the K, the faster the reaction. And remember, a long time ago, we talked about factors that affect rates, concentration, physical state of reactants, temperature, and presence of the catalyst. So those things affect reaction rates. Physical state, temperature, and presence of the catalyst affect the rate constant. And so this actually gives you the energy of the molecules as fraction of molecules having a certain kinetic energy as a function of kinetic energy. And so T1 is the lowest in energy, and then as you raise the temperature, so T2 is a little bit higher and T3 is a little bit higher, notice that you're going to a higher average kinetic energy. Also notice that the distribution of kinetic energies get bigger, consistent with higher temperature means higher entropy. Now using the Arrhenius equation, if we plot the rate constant as a function of temperature, we get a nice exponential. And so again, for all reactions, higher temperature always means faster reaction. Now if we take the Arrhenius equation, K equals e to the power of minus EA over RT, and we take the natural log of both sides, we get natural log K equals natural log AE over RT. Now natural log of A times B is the equal to natural log of A plus natural log of B. And then the natural log of e to something is just that something. And so the bottom equation, we have natural log of k equals natural log of a minus ea over rt. Now you should actually recognize this as the equation for a straight line. And so if you think about y as being natural log of k, mx is minus ea over rt, and b, your y-intercept, is actually natural log of a. And so if you're able to measure the rate constant as a function of temperature, and then you plot the natural log of k versus 1 over t, you should get a straight line. And then the slope of that line is going to be minus EA over R. And so you can actually determine what the activation energy is. The y-intercept would actually be natural log of A. And so Arrhenius equation, very important, shows us that the higher the temperature, the faster the reaction, the lower the activation energy, the faster the reaction. And again, using the Arrhenius equation, we can actually determine the activation energy if we plot natural log of k versus 1 over t. Now if we look at some biomolecular reactions, bi meaning two, so two molecules reacting, two things we have to notice is that one, the energy of the molecules have to be high enough to overcome the barrier for the reaction to proceed, and the molecules have to collide in the correct orientation.
For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting.
And so again, the exponential term in the Arrhenius equation is actually related to the percent of molecules that have enough energy to overcome the barrier.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreact.
And the A term is related to what percent of the collisions actually have the correct orientation. And so we can look at another example.
For some complex reactions, such as that between potassium atoms and methyl iodide, the relative orientations of the reactions becomes important. Only when the potassium atom collides directly with the iodine atom will the reaction take place.
And so a reaction like this, we need both to have enough, the reactants need to have enough energy to overcome the barrier and have to collide in the correct orientation. And so the Arrhenius equation helps us understand the effects of temperature, activation energy, and the presence of a catalyst on the rate constant and the reaction rate. I hope that was helpful.